All right, we had started chapter 6, in which we were discussing effect of noise on amplitude modulation or on angle modulation system. So first of all, we just discussed on amplitude modulation as in the last lecture. So if you could remember, we had this example that we did in the last lecture, 6.1.2. The steps I explained to you in the last lecture, but there I assume that sinc square Fourier, is triangle, and the mathematical details I said that you might have studied in your previous course, or I will revise. So a lot of the students are not able to recall. So just for their remembrance, we all know sinc gives us a rect in frequency. So sinc square in time will be multiplication in time. This will be convolution in frequency. And so sinc square, convolution of two rects gives us a triangle. Okay, you can use this notation or as well as this notation. Both are the same, triangle, and this is a rect. And you can apply duality. Then you can very well see that triangle in time is actually equal to sinc in frequency, sinc square in frequency. So they both are dual. They also make up a very important set used in communication. After rect, this is the next important transformation that you should be well versed with. So we have seen that sinc square gives us a triangle. So if I scale my sinc square by 10 to the power 4, then from the Fourier transform property that frequency will be, if it is multiplied here, they will be divided here, as well as in the outside. Scale by 16 is scale by 16. So this comes out to be its Fourier transform, as this was an autocorrelation. So this will be its power spectral density. Now, what is the shape of this triangle signal? It is actually given as follows. So this is T domain. It goes from -1 to +1. Height is 1. Similarly, in F, triangle F will be actually again a triangle from -1 to 1, 1. We know that this triangle is actually given by convolution of two rects in F. So if you scale triangle by 10 to the power 4, this means that its width is now 2 to 10 to the power 4, because remember when triangle was F, so it was F over 1 and it was just representing the positive frequencies. So if we extend by 4, this means is still representing the positive frequencies. So the total width will come out to be 2 into 10 to the power 4. This is in contrast to the representation used for a rect, because in rects, whatever the width here, F over the width, that's whatever the term F over or the denominator term below the F, that same terms comes here. So if I have triangle of F, this means I will have a rect whose width will be 1. If it is rectangle F over 4, so its width will be 4. But here you can see if it is 1, it only represents this much width. Because because of convolution, the width of the rects when they represent a triangle, they convolve and then the triangle widths become double. So 10 to the power 4 means that its pictorial description will have a width of 2 times 10 to the power 4. And scaling there, it will just scale 1 to 16 10 to the power minus 4. Now, some students might ask why we are getting this type of convolved output, that is in terms of a triangle. So you can see that this triangle is actually convolution of this rect with this rect. So this rect is stationary in convolution x of tau into h of t minus tau. So first of all, let us say t is 0. So h of minus tau, it will be just the same signal because rects are symmetric, half into half. Now when you have f0, which means you are not shifting, t0 lene f0, but here I am convolving an f, that is why I have said f0. So both the rects will be exactly overlapping one another with full overlap, and you can see the area under the curve or the output of the integration will be 1. This is the maximum value. Now as you will shift your h towards the right or towards the left, towards the right, you know, you have to put 1, 2, 3, and so it will be minus h1 minus tau, it will be shifting towards the right. And once you shift it so that its end comes to 3 over 2, this means h has been shifted from h0 minus tau to h1 minus tau. So when it is at h1 minus tau, then you can see that this width will be going from half to 1.5. The original x of t was from minus half to half, so there is no overlap. So overlap decreases when the shift is 1, or overlap becomes 0 when the shift is 1. Similarly, when the overlap becomes 0 when the shift is minus 1. That is why the convolution is 0 at plus 1 and minus 1. Below, you know, it is moving in a linear fashion. That is why you get a straight line. You can also find line if you do the integration properly. So I hope it gives us your revision for the important function of rect as well as triangle in terms of sec and sec squared. This is the second section. In this section, we will start with the study of effect of noise on angle modulation. So we know angle modulation was studied in chapter 4, that consisted of phase modulation and frequency modulation. Now, in that you have the modulated signal and you have the noise. Noise was just adding in an additive fashion to the modulated signal. But what happens in FM? You can very well see in FM modulation, remember that the message signal is present in the phase. It might be the instantaneous frequency, or it might be the instantaneous phase message signal. So whatever the change is coming in the phase of the modulated signal. So noise has to be added to the amplitude and the message information is contained in the frequency of the modulated signal. So you know the noise that will actually affect the phasor part. So the message signal is contaminated by the noise. Alright. So but the message signal is present in the phasor part of the angle modulated signals. Alright. So yes, the noise will also affect the amplitude, but we have seen in the last chapter 4, in last chapter 4, that whatever those changes, those changes can be nullified by using a hard limiter, because the amplitude should not have changed. So you can get rid of all those effects. But the noise that comes inside the phase, because phase contains the message signal, okay, that will affect the signal. So the added noise changes the frequency of the modulated signal. Yes, because noise changes the message signal. Message signal is actually changing the phase or the frequency of the modulated signal. And the frequency, you know, it can be described by zero crossing, how many times it crosses the zero. So the effect of additive noise on the demodulated FM signal can be described by the changes that it produces in the zero crossings of the FM signal. So the FM signals zero crossing will change, and that is changing because a message signal is added upon by noise, but that additive noise plus message is present in the phase of the signal. It will actually change the phase or the frequency of the modulated signal. So figure 6.1 shows the effect of additive noise on zero crossing of two frequency modulated signal, one with high power and another with low power. So you can see this is the change in low power, and this is a change in high power modulated signal. So you can see the effect in high power is not that significant as compared to the effect in low power modulated signals. So it also gives us an idea that noise in FM system is different from noise in AM system, and also that noise in low power FM system is severe as compared to effect of noise in high power FM system. So in low power signal, noise will cause more changes in the zero crossings, and then we will be presenting the analysis which will verify our observations. So the block diagram for the receiver of a general AM signal is shown in figure 6.2 that we have already covered in chapter 4. So first of all, you will have a band pass filter that will restrict the signal along the frequency of the bandwidth of the modulated signal. It will restrict around that. Then you will have an angle demodulator that will give you the message signal, and then the message signal, we know it will be present only around with W bandwidth, so you will pass it through a low pass filter, so that will give you the a message signal. So this was my modulated signal, where we know this phi t could be represented as integral of mt for FM, and directly proportional to phase is directly proportional to mt in case of PM. So the additive white Gaussian noise is added to U of t. The result is passed to a noise limiting filter whose role is to remove the out of band noise. So we know that noise n0/2 extends for all the frequencies. So when the noise is added with the incoming modulated FM or PM signal, you will have a signal plus this noise which extends through for all the frequencies, white noise. But when you will pass through a band pass filter, it will only extend around FC, and roughly the bandwidth is given by the Carsten's rule. So band pass filter will just give you the set of frequencies around your carrier frequencies with the bandwidth roughly equivalent to the Carson's bandwidth. So it will eliminate the out of band noise. Hence the noise output of the filter is a filtered process. So what will be the noise? What will be the output? Output will be the modulated signal plus the band pass noise. So after the band pass filter, the noise will be still high frequency, present around FC with bandwidth of BC for positive and negative frequencies, but still it is present around FC. So it is a band pass noise having a bandwidth of BC and BC for negative and positive frequencies. So we know any band pass process can be represented in terms of its low pass, in phase and quadrature components as follows. This we have studied in chapter 2, as well as it was revised in chapter 5 with respect to noise presentation. So again, analysis could be quite involved. We will try to use some approximations to get a generalized result. So first of all, we assume the signal power is much higher than the noise power. Signal power is much higher than the noise power. Then in that case, first of all, what is a band pass noise? So we know band pass noise is this NT. It can also be represented like this, but we can also represent it like this in terms of its envelope and in terms of his phase. This was also studied in chapter 2 as well as revised in chapter 5 with respect to noise. So yes, NT can also be represented as follows, but it can also be represented as follows. Both are correct representations. Now, so what is VNT? VNT will now be the envelope of the noise, and phi and T will now be the phase of the noise. And what is this noise? This is the band pass noise process. And yes, we assume that the signal amplitude is much greater as compared to the envelope of the noise or the noise amplitude. Or you can see the carrier amplitude is much greater than the noise amplitude. So he says with this assumption, this will be the phasor diagram of the signal and the noise. So actually, many of the steps are missing in representing this diagram. He has taken a direct approach. So that is why I will try to explain this with my own figures. And if you have any question, you can ask. Ari 169, do you want to say something? All right. So if someone has any questions, you can ask now. All right, no questions. So let us try to understand the phasor diagram of representation of the band pass noise process with the modulated FM signal. Now, so what is my FM signal? FM signal is amplitude is AC, and I know the cosine part is 2 pi FCT plus phi t, where phi t, it could be directly proportional to the message signal for PM, or it could be, integral of the message signal in terms of FM. So I can write my modulated signal as AC cos 2 pi FC phi t. So, in phasor diagram, 2 pi phi FCT is there, but what is the phase? Other than 2 pi phi FCT, 2 pi FC is phi t. So I can just write my modulated signal as AC with an angle of phi t. But 2 pi FC is present for all the vectors. Now, what I do, I know that my signal is being added by a band pass noise, as we just saw here. So we have our modulated signal, which is just AC and this phi t angle, added with this band pass process, which I can represent as VNT. Again, this is common with a phase of phi nt. So I can just write, I have this noise VNT, and it makes a phase phi nt. Okay, with the x-axis, you can just, property of shifting of vectors, you can just shift the vector here, so it makes an angle phi nt. So the resultant vector will be sum of AC plus Vn, so that will be your RT vector. All right. Now here we are interested in finding actually this angle. So you can see that this is phi of nt, this will be 180 minus phi nt, while this alpha will be equal to 180 total minus phi t minus 180 plus phi nt. This means this alpha comes out to be phi nt minus phi t. All right. Now what I do, so I found this angle and I extend this line. This line was this phi n vector. This was this phi n angle. But I get rid of this line. I just concentrate on these two lines. This line is here and this line goes like this. This is what I am drawing here. This is a line representing the phi n angle here. Is going like this, while this line representing AC is making an angle phi nt minus phi t. If this is phi nt minus phi t, this angle, because of alternate angles, will also be equal to phi nt minus phi t. Now here this is Vn. Previously Vn was represented in terms of phi n angle, but now we have a different angle, which is phi nt minus phi t, that comes because of the intersection of these two lines. So if I take its VNT along this straight line, so this will be VNT cosine of phi nt minus phi t, while along this line which is perpendicular to this line, this will be equal to VNT sine of phi nt minus phi t, just by the the Pythagoras theorem or representation of vector in terms of in phase and quadrature components. So now what I do, now I write my R of t, okay, in its envelope and phase notation by assuming that amplitude of RT is approximately equal to AC plus this thing Vn cos of this, okay, because we are saying that this Vnt is very small, because Vnt is represented by its cosine and sine components. So we are taking the cosine component, but we are neglecting the sine component in the amplitude. So we are assuming that this is the amplitude approximately, because you can see Vnt is very small, so its sine component also with this angle will be more smaller. So we can neglect this in terms of amplitude, but we will take care in terms of phase. Amplitude comes out to be AC plus Vn cos of phi n minus phi t, or AC plus Vn taken to the x or taken to its phasor in phase part. This will be Vnt times cosine of this angle, which is phi nt minus phi t. This is the amplitude. Okay. Times. So I again represent this in the phasor notation as we were representing this in terms of representing this in terms of its envelope and phase. So and this is the envelope now approximated, and the phase cos 2 pi of ct is already there, but the additional phase is phi t plus beta. So you can see phase of RT is taken exactly, which is phi t plus this beta angle. Now, how can I find this beta? So we can very well see that this total angle, this total triangle is because this is a 90-degree angle. So this is a right angle triangle, all right. And I can write my tan beta as perpendicular over the base. So perpendicular is sine Vnt sine phi n minus phi t, while base is AC plus Vnt cos phi n minus phi t. So I can write this as tan beta as the perpendicular over the base of my designated right angle triangle. Now we know that tan beta is sine beta over cos beta, and we know that beta is a very small angle. That you can see why, because again we know AC is much greater than Vnt, or you can say the AC plus Vn cos is much greater than Vn sine, and we know actually this happens because AC is much greater than Vn. So beta will be a small angle, because AC is much greater than this, all of this. Beta is small, I can write my tan beta as sine beta over cos beta, sine beta over small angle cos 0, which comes out to be 1. So sine beta, but we know sine of a small angle is actually the angle itself, beta. So I can write tan beta as beta, and tan beta was this, so this total value will become beta, all right. So this total comes out to be beta, but here again I can say that the AC is much greater than this term, so I can neglect this term. So Vnt over AC sine of this is equal to beta. Now with this value of beta, I will substitute this in the approximated R of t. So this remains the same, but here your beta will come out to be this term. This term will come here in terms of beta. And everyone is understanding at this point? So we have got up to this point. Okay, we have proven up to this point. If any student has any question, he can ask. Alright. Acha, I was actually noticing your attendance, and I realized that many of the roll numbers are missing in the attendance list, even in LMS. So I inquired and I was told that all those students who have not been able to pass their probability course, they were not admitted into the into this course. Is it true, Hamza? Hamza bin Abdullah, CR of D section, that those students who have not passed the probability, they are not present in these sections. Haji Hamza, can you hear me? Roll number 172. लगता है आज भी इनका कुछ स्पीकर या माइक खराब है, आवाज नहीं आ रही, इनको हेडफोन खराब है. Alright, Salman, can you hear me? Salman Jameel.
जी सर.
वो हमजा साहब से कहें कि हर दफा तो फोन नहीं खराब होना चाहिए उनका, ये हेडफोन. चलें खैर, वैसे मैं कह रहा था कि have you noticed that many of the students are missing? So those students who have not passed, they are not present in this course. Is it true from your side also?
सर मुझे इसका आइडिया नहीं है.
अच्छा. Have you got the result of probability?
जी सर वो आ गया.
अच्छा अच्छा अच्छा. चलो, thank you.
सर मेरा ख्याल है प्री रिक्विजिट खत्म कर दिया.
प्री रिक्विजिट खत्म कर दिया? अच्छा, आपको कब पता चला इस चीज का?
सर ये नोटिस आया था हफ्ता पहले.
पहले तो फिर आपको पुरानी नॉलेज है. मैं तो अभी गया था ये इसी हफ्ते, तो पहले मैंने LMS में लिस्ट देखी, फिर मैंने इनसे पूछा भी, तो कहा कि हाँ जी वो हमने नहीं पास होने दिया उन लोगों को, मतलब जिसके प्री रेक पास नहीं उसको अगले कोर्स में नहीं प्रमोट किया. तो इसलिए मैं देखा ना आपके LMS में रोल नंबर भी काफ़ी कम है. इधर वो मैं अटेंडेंस लगाने में मुझे प्रॉब्लम आ रही है, यहाँ पे बहुत से लोग अटेंड कर रहे हैं मगर वो LMS में है ही नहीं, तो ज़ाहिर उनकी अटेंडेंस ही लगी जब तक वो LMS में नहीं होंगे. Well, you can if you have that notice, you can send me also. Okay, so we will check it, but this was up to my knowledge. All right, so we have done up till this equation. The received signal envelope and phase has been approximated, and this expression has been found. Now this signal, which is the output of the the band pass filter, and now it will go to a demodulator. So we have either a phase demodulator for PM systems, or we have a frequency demodulator for FM modulated signals. So modulator or demodulator, it gives you back the message signal which was actually hidden inside the phase of the FM or PM signal. So demodulator will give you the phase, while the demodulator for a PM will give you the phase because the message is contained in the phase. While the demodulator of the FM, okay, it will actually give you the derivative of the phase, or 1/2 pi derivative of the phase, because 1/2 pi derivative of the phase is actually the message signal. So you could see in your, for example, from a previous chapter 4 knowledge, in PM the phase is directly proportional to MT, but in FM the difference of the instantaneous frequency is directly proportional to directly proportional to the message signal. All right, and this difference in frequency is 1/2 pi derivative of phi t. All right, so this means that phi t is integral of MT and all that, but you can very well see that the demodulator for an FM system will give me this as an output, or it will take whatever the phase is there present in the modulated signal, it will take its derivative, divide by 1/2 pi, so this will be the output. But for PM systems, the output will be just whatever the phasor part, that will be the output. But in FM system, the phasor part has to be taken its derivative with time, divided by 2 pi, and that will be the output of the demodulator for an FM system, because for FM this is the signal, for PM this is the message signal. So we know that for PM this is the phase, but for FM actually the instantaneous frequency is the message signal. So the phase will be actually 2 pi into integral. All right. So phase phi t is actually equal to 2 pi integral of kf mt. Kf is constant, so 2 pi kf integral of mt. That is the phase of the FM signal. This is the phase of the PM signal. This is the phase of the FM signal. Now the output of the demodulator will be the phase. The phasor part in the the modulated signal will be the output of the PM. This is the output. But in FM, this is not the output, because FM output of the demodulator should be KFMT, but KFMT is 1 over 2 pi derivative of whatever the phase. So whatever the phase derivative 1 over 2 pi. This will be the output of the FM demodulator. Now you can very well see that phi t is equal to for PM phi t is kpmt, and if I take its derivative, so this will become 1 over 2 pi d by dt phi t. But what is 1 over 2 pi d by t d phi t? So you can very well see that 1 over 2 pi d by dt phi t is equal to kfmt. Right? So we'll get kfmt here, and this will be 1 over 2 pi derivative of this term. This is PM and this is FM output of the modulator. So I can call this term as y and t. So I'll just replace this by y and t. This is also y and t. This will be 1 over 2 pi d by dt y and t derivative. So here you can see that these first terms in PM and FM, they are the desired message signals, while the second terms, they are the noise. And we can also observe, because y of nt is coming in both the expressions. So what is y of nt? Y and ft, which is a noise, is actually 1 over AC. This means greater AC, less noise. Smaller AC, large noise. So that we actually observe in the beginning of this section, that if you have a large high power signal, which means it will have a large AC, you get low noise. But if you have a low power signal, which means you have low AC, you will be getting more noise. All right. If someone has any question, he can ask. अच्छा,
सर।
वालेकुम सलाम व रहमतुल्लाहि व बरकातहू। हाँ जी हमजा साहब, आप बीच में हर जगह गायब ही हो रहे हैं।
सर मेरे हैंड फ्री क्राइसिस आए हुए हैं सर असल में।
तो कब से चल रहा है आपका क्राइसिस? तो रमजान के वक्त भी था।
नहीं सर, असल में निकलना नहीं हो रहा मेरा सर, ड्यू टू सम फैमिली प्रॉब्लम्स।
अच्छा चलिए अल्लाह ताला सबको
सर आप प्री रेक का पूछ रहे थे, प्री रेक सर खत्म कर दिए डिपार्टमेंट ने सर।
अच्छा, मैं तो मंडे को गया तो उन्होंने मुझे बताया कि
नहीं सर नोटिफिकेशन आ गया उनका, नोटिफिकेशन सर प्री रेक्स का आ गया हुआ है। प्री रेक्स सर उन्होंने खत्म कर दिए। डीन साहब ने सर कहा था ऑन रिक्वेस्ट ऑफ स्टूडेंट्स कि इस दफा समर सेमेस्टर की वजह से खत्म हो गए हैं सर।
अच्छा, ये कब आया आपको से आपके डीन साहब की तरफ से?
सर ये काफी इसको खत्म हुए हुए ये मैं सर आपको नोटिफिकेशन
नहीं मुझे वैसे बता
कर देता हूँ सर।
नहीं वो आप कर दीजिएगा, वैसे मैं पूछ रहा हूँ आपको अगर कुछ याद। रमजान में हुआ था ये, रमजान के बाद हुआ?
सर मैं आपको भी बता देता हूँ, एक मिनट।
नहीं इतना कोई टाइम नहीं, मैं तो वैसे ही चले अंदाजा लगा रहा था। ठीक है, मैं मंडे को
सर 3-4 दिन पहले हुआ।
हाँ ये फिर हुआ होगा ना। हाँ फिर चले, हो सकता है
सर 3-4 दिन पहले ही हुआ।
हाँ फिर ठीक है।
लेकिन सर मतलब उनको नोटिफाई करना चाहिए था।
नहीं जब मैं गया था 3-4 दिन पहले ही, मैं मंडे को गया हूँ ना भाई, संडे तक तो वैसी ही छुट्टियां थी। तो मंडे को मेरी सुबह बात हुई थी डिपार्टमेंट में। तो जाहिर है अगर उन्होंने मंडे को ही फैसला किया होगा तो वो उस वक्त तक तो कन्वे नहीं हुआ होगा। अगर
मोस्ट प्रोबेबली सर इधर
तो चलो ठीक है, फिर तो
हो गए हैं।
मैंने कहा मुअम्मा हल हो गया है। ठीक है ना, मैं अटेंडेंस लगाने मुझे काफी प्रॉब्लम आ रही थी ना कि स्टूडेंट सारे इधर तो आ रहे हैं और एलएमएस में अक्सर गायब है, यानी कि पूरी लिस्ट ऑफ रोल नंबर्स
सर
गायब थे।
एलएमएस में गायब है सर, स्टूडेंट्स मेरे पास आ रहे थे, मैंने आपसे बल्कि रिक्वेस्ट इस पर भी करनी थी कि सर जो एडीसी की थ्योरी की क्लास है उसके अंदर सर सीट्स कम है सर, इसकी काइंडली सर अगर सीट्स आप बढ़ा दें सर।
मैं समझा नहीं, सीट्स क्यों कम है?
सर एलएमएस के ऊपर जो सीट्स रजिस्ट्रेशन सीट्स हैं वो कम आ रही हैं।
अच्छा,
वो सर
मुझे तो
स्टूडेंट्स
लग
को
रहा है कोई
जगह
स्टूडेंट ही
फिल होगी
रजिस्टर्ड नहीं है। अगर आप देखें वो तो कम 50 तक अलाउड है ना, वो तो बिल्कुल ही कम है स्टूडेंट्स।
नहीं
मेरे
नहीं
पास
सर
अगर
सर क्योंकि समर ऑफर नहीं हुआ, या मुझे नहीं पता सर ये सब्जेक्ट समर में ऑफर होता है नहीं होता, लेकिन सर समर ना ऑफर होने की वजह से
समर में तो
सर
ऑफर नहीं होगा ना, बहुत मुश्किल लग रहा है ना, क्योंकि सारा तो हम समर में पढ़ते ही रहेंगे।
जी
आप देखिए ना, मई स्टार्ट हो गया, इस वक्त हमारा तकरीबन क्या मतलब 6 वीक चल रहा है, 13 लेक्चर तो 6 वीक्स। हाँ तो तकरीबन देखिए ना 9 वीक्स तकरीबन रहते हैं, चलिए 8.5 वीक से 9 वीक से पक्के हैं,
बिल्कुल
तो
सर
9 वीक्स
ऐसे
का
ही है।
मतलब है 2 महीने तो लग गए। तो जून मई भी तकरीबन आधा तो गुजर चुका है ना, तो मतलब जुलाई
बिल्कुल
तक तो
सर।
पक्का जाएगा। अब अगर जुलाई
सर
तक आपका मेन जा रहा है तो समर ने कहाँ आना है? अब ये तो
सर
अगस्त में
हमारा
तो समर
मेन ये
करेंगे।
अगस्त तक जा रहा है, अगस्त के शुरू में जा रहा है ये,
हाँ अगस्त में बीच में मिड
जुलाई
टर्म भी
के एंड
होगा।
में अगस्त के शुरू में एक्चुअल टाइम है। सर दूसरा आपसे ये पूछना था कि सर मिड्स का हमारा सर सर क्योंकि 16 लेक्चर अभी तक पूरे नहीं हुए, आज ये इसका 13वां लेक्चर है सर, तो मिड सर 16 तक होता है लेक्चर सर, तो
हाँ
वो
हाँ,
उसके
अभी
ऊपर
तो
सर
मिड
आपसे
टर्म आपका
पूछना
नहीं
था।
होगा। वो तो अभी आपको पता है ना, पिछले इतने पड़े हुए जिनका मिड लेना है इन्होंने, वो तो इसकी वजह से, लॉकडाउन की वजह से सारे बैठे हुए हैं।
नहीं
वो जो
सर वो कहीं ऐसे ना हो गए सर हम जाएं तो फौरन सर 1 वीक नोटिस के ऊपर मिड कह दें, या ऐसे को काम ना हो जाए सर।
नहीं मैं समझ, आप क्या कह रहे हैं?
सर 1 वीक नोटिस के ऊपर मिड ना हो जाए सर, कहीं सर आपको कोई आइडिया
नहीं
मिड के
मेरा
बारे
नहीं
में
ख्याल
सर?
इतना जल्दी हो सकता है, क्योंकि मैं आपको थोड़ी सी बता रहा हूँ कि मैं सर जैसे मास्टर्स की क्लास पढ़ा रहा हूँ, या जो
जी
फाइनल
सर।
की क्लासेस हैं उनके तो इस वक्त हम लोग तकरीबन 21-22 लेक्चर कर चुके हैं, और अभी
जी
तक
सर।
उनका मिड टर्म ही नहीं हुआ। तो
यस सर।
जो भी आपको बताया एसओपी के अंडर पहले तो उनका मिड टर्म करना पड़ेगा हमें, तो उसमें भी कम से कम वो आपको पता है कि गैप रखो और ये रखो, उसमें भी 1-2 हफ्ता लग जाता है। तो
यस
इसलिए
सर।
अभी तो मुश्किल है। आपका ये हो सकता है कि ये यानी कि 8 वीक के बाद जब आपके 16 लेक्चर्स हो जाएं तो
जी
फिर आपको मिड टर्म आ सकता है। अभी तो मिड टर्म आना बिल्कुल इम्पॉसिबल है जब तक आपका कम से कम 8th वीक कंप्लीट नहीं होता। अभी तो आपका देखिए ना 7th वीक चल रहा है इस वक्त, तो 13
बिल्कुल सर।
लेक्चर्स हैं आपके, मतलब अगर 14 भी कर लें तो अभी भी कम से कम भी 1-1.5 हफ्ता तो पक्का है। उसके बाद फिर अभी तो उनके नहीं शुरू हुए, मेरा नहीं ख्याल अभी फौरन
बिल्कुल
होगा
सर।
आपका। वैसे अभी वो फैसला आने वाला है, जैसे पंजाब यूनिवर्सिटी में तो इन्होंने 24 से यूनिवर्सिटी, यहाँ भी तो एनसीओसी का आज भी अखबार में मैंने पढ़ा था, यूनिवर्सिटी को तो खोलने का कह दिया उन्होंने, मगर आई थिंक
सर
क्लासेस
वो
ऑनलाइन
यही
है। वैसे
सुन रहा
यूनिवर्सिटी
है
में लैब वैब तो खुल जाएगी 24 से।
24-25 जून का मैंने भी सुना है, यही सुना है सर।
हाँ नहीं वो तो आज अखबार में मैंने देख लिया है, यूनिवर्सिटीज को
जी
कह रहे हैं
सर।
कि ओपन कर दें, लैब्स तो खुल जाएंगी सारी। अब वो उसमें ये है कि इन्होंने डिसाइड करना है कितना ऑनलाइन रखें कितना ऑन कैंपस रखें, और एग्जाम से फिर ऑन कैंपस बिल्कुल हो सकते हैं, मगर आपका ज़ाहिर है 8 के
बिल्कुल
बाद
सर।
होगा। और दूसरी कंसिडरेशन मुझे ये कि 8 के बाद भी फौरन होना मुश्किल लग रहा है, क्योंकि पिछला
सर
अच्छा
मुझे
खासा बैकलॉग है। जिनका वो फाइनल भी आने लगा है, जिनका मिड टर्म भी आ रहा है, तो उनका तो पिछले से काफ़ी डिले होता गया, तो पहले उनका होगा फाइनल ईयर का या मास्टर्स वालों का, उसके
जी
बाद
सर।
आपका मिड टर्म होगा, वो भी गैप रखना पड़ता है आपको पता ही है। तो
बिल्कुल सर
मेरे
ऐसे
ख्याल
ही
इतना
है
जल्दी
एसओपीज
होगा, पर
वगैरह की
आप
वजह
लोग
से।
ये रखें कि भाई 8 के बाद कभी भी हो सकता है, और विद रिस्पेक्ट जो भी कंडीशंस हैं उसके साथ भी थोड़ा सा लेट हो
बाकी
जाए।
सर वो प्री रिक्विजिट्स वाली की बात सी सर, मैंने भी आपसे ये बात करना था कि सर आप काइंडली वो एक्सटेंड वो सर बढ़वा दें सर, सीटिंग स्ट्रेंथ बढ़वा दें सर क्लासेस की अपनी सी और डी की
मुझे
सर।
ना कोई ऐसा, मुझे इसका इन चीज़ों का इतना पता नहीं कि इन्होंने क्या रखा हुआ है। वैसे तो स्टूडेंट्स इनरोल्ड, मुझे नहीं समझ, जो रेगुलर स्टूडेंट्स है वही नहीं इनरोल हो पा रहे।
हाँ जी सर, नहीं हो पा रहे एनरोल सर, वो आपके पास यहाँ
तो फिर
बिल्कुल ऐसे ही है,
आपके
नाम यहाँ
चेयरमैन
पर
से
आ रहा
बात
होगा, वहाँ नहीं हो रहे।
कि इसमें मेरा तो कोई नहीं होता, मैं तो ही कंट्रोल करता हूँ एलएमएस में रजिस्ट्रेशन कि हो या ना हो। ये तो डिपार्टमेंट और आई थिंक बेसिकली डिपार्टमेंट का या रजिस्ट्रार का इनका मतलब
सर वो
इनसे बात
पहले
कर।
कोऑर्डिनेटर साहब को कहते थे, तो वो कोऑर्डिनेटर साहब कहते हैं कि वो सेमेस्टर सेल वालों से राब्ता करें सर, वो सेमेस्टर सेल वाले तो सर ऑनलाइन पर्टिकुलर सर करना पड़ेगा उनसे सर, वो स्टूडेंट्स इतने ज़्यादा हैं सर, तो अगर आप एज सर टीचर रिक्वेस्ट करते हैं इस बात को वेरीफाई भी हो जाएगी कि सर वाकई में स्टूडेंट्स काफ़ी ज़्यादा हैं।
हाँ नहीं आप ऐसा कर लें, मेरा जो आपको मशवरा होगा कि मैं इस बात को सेकंड तो कर सकता हूँ,
हाँ जी
मगर
सर, आप
हाँ
सेकंड कर
मगर ये कि
दीजिएगा।
आप ना पहले जो है ना एक चेयरमैन साहब के पास डायरेक्ट जाएं
जी
उनसे
सर।
कहेंगे सर ये हमारे इतने स्टूडेंट्स हैं, अगर आप कहें तो मैं आपको LMS की जो लिस्ट है मेरे पास, तो जो
जी
क्या
सर।
कहते हैं इसको, जैसे मेरे पास जो अटेंडेंस आई
अटेंडेंस
है
लिस्ट
वो मैं आपको
सर,
ईमेल,
आप
उसमें तो
काइंडली वो
काफी
शेयर कर
कम है
दीजिएगा
बंदे।
सर।
मैं तो हैरान हूँ, उसमें स्टूडेंट्स ही नहीं है, मैं तो अटेंडेंस लगाते हुए मुझे वही आई थी, हो क्या रहा है इधर।
सर मुझे 2-3 दिन बड़ी सर इसकी गई हैं, कंप्लेंट्स आई हैं स्टूडेंट्स की तरफ से कि हम एनरोल नहीं हो पा रहे, क्योंकि सर वो इन्होंने फी का जो था लास्ट डेट वो आगे बढ़ा दी थी, तो सर वो स्टूडेंट्स इस वजह से
चलिए
सर
फी का तो
एनगेज
समझ
नहीं
आता है ना, वो तो फिर उनकी अटेंडेंस भी लग
सर,
जाएगी जब।
उसके बगैर सर रजिस्टर्ड नहीं हो पाता।
तो ये आप ना थोड़ा सा चेयरमैन साहब को एक
मैं
एप्लीकेशन लिख
सर
के
कर लेता हूँ।
कि सर जी इतने स्टूडेंट्स का तकरीबन जैसे 20-30 का मसला है, मुझे नहीं पता कितनों का
जी
मसला
सर।
है, तो उनका
सर
ये
इतनों
मसला
का
है कि वो
तकरीबन
रजिस्टर
है।
नहीं हो पा रहे, और जहाँ तक मेरे पास नॉलेज है इस वक्त उधर तो सीट्स भी अवेलेबल हैं, वो तो कोई बंदे ही नहीं है उसमें LMS के ऊपर।
सर वो
मैं
स्टूडेंट्स
थोड़ा सा
तो जो
दिखाता हूँ।
मुझे कह रहे थे कि सीट्स अवेलेबल नहीं है, चलें सर मैं क्रॉस चेक कर
अच्छा,
लेता हूँ इसको।
नहीं स्टूडेंट्स कह रहे थे चलो उनके पास भी कुछ बात तो होगी, मैंने कैसे पता किया था।
सर वो वहाँ स्ट्रेंथ आ रही होती है, वो स्ट्रेंथ सर 45 लिखी होती है, वो 45 की 45 ही रहती है, तो सर जितने
अच्छा
मर्जी इनरोल हो जाए सर, वो उनका कोई बग वगैरह है इनके एंड के ऊपर शायद।
अच्छा, चलो ठीक है, तो मैं इसको देखता हूँ फिर। मैं
थैंक
मुझे
यू
अभी
सो मच सर।
यानी देखने मैं अभी मैं आगे नहीं, वो जो एप्लीकेशन है मैं इसको सेकंड कर दूंगा, तो
सर
मैं
आप
ये देख
सेकंड कर
लेता कि
दीजिएगा, मैं
LMS
आपसे
में
सर शेयर कर लूंगा भेजने से पहले।
हाँ हाँ नहीं ठीक है, वो तो कोई मसला नहीं। तो चेयरमैन साहब का वैसे भी है वो ज़ाहिर है, ये तो एक जेन्युइन मसला है।
जी
तो
सर।
जैसे लास्ट टाइम देखे ना EMT में उन्होंने 3 सेक्शंस बना दिए थे, याद है आपको?
सर EMT में 3 बने, MPS
मतलब
के
मेरे
तकरीबन।
मेरे 3 हो गए थे, मैं तो
जी
तीन
सर।
तीन देख रहा था, रिपीटर्स को उन्होंने डाल दिया था, फिर वो
सर
बहुत
वो
मसला
ई
भी हुआ था।
सेक्शन बना दिया था।
हाँ हाँ ABCDE बना दिया था, हाँ
जी
जी।
सर।
पर करने के तो बहुत कुछ होता है, मुझे नहीं पता कि कहाँ फंसे हुए हैं। चलो खैर ठीक है, आप अपने से एप्लीकेशन बना के चेयरमैन साहब को पक्का ही दे दें, मुझे
मैं
पढ़वाए ना
सर
पड़े कोई
आपके
ज़रूरी
साथ
दे दें उनको,
उनसे पहले भी
और
सर
मुझे उसका एक
सर
कॉपी
आप
कर दें कि सर
श्योर
ये
सर,
मसला है, फिर मैं ये कि उस पे उसके बिना पे मैं डिस्कस कर सकता हूँ
मैं सर आपको उस
चेयरमैन
पे
से या
कर
लतीफ़
दूंगा
साहब
सर।
से। चलें
थैंक यू
ठीक
सर।
है। अच्छा ये रमज़ान नवाज साहब भी यही कह रहे हैं कि जी फी अपडेट होगी तो रजिस्टर हो जाएंगे। चलें,
जी
अगर
सर।
फीस से अपडेट होने से तो जाए तो अच्छा है, मगर आप तो कुछ और कह रहे हैं कि रजिस्टर नहीं हो पा रहे।
सर वो उनको सीट्स वो लेस का कह देता है, लेकिन सर देख लेते हैं ओवरऑल स्टूडेंट्स का, क्योंकि सर वो
चलो
उनकी
देख,
अटेंडेंस मिस हो रही है, तो वो स्टूडेंट्स अटेंडेंस की वजह से परेशान होते हैं।
हाँ मैं भी देख रहा हूँ ना कि बंदे ही नहीं है, खाली खाली है सारा, ज़्यादा तो रिपीटर्स ही नज़र आ रहे हैं, आपके अपने रोल नंबर से कम थे वहाँ पे।
जी सर
मुझे
हमारे
याद आ रहा
काफी
है,
कम
बाकी
हो
मैं
गए।
गलत, मैं चेक कर लूँगा इंशाल्लाह, एक दो अटेंडेंस लगा के मैं भेजता हूँ, तो उससे
श्योर सर।
इस पे अपलोड कर दूंगा ये आपके MS टीम पे, तो आप लोग देख सकते हैं कि क्या सिचुएशन है इस वक्त LMS की।
थैंक यू सर।
अल्लाह हाफ़िज़। अच्छा नाउ कमिंग बैक टू द लेक्चर, हम लोग कहाँ पे थे? अच्छा अच्छा, so we were actually discussing the observation with respect to the mathematics that we have developed here, that greater the power or greater the amplitude of AC, less will be the noise. And we know in AM systems noise is independent of the signal, okay? But here you could see that the noise is dependent on the amplitude or the power of the signal. This is a huge difference between AM and FM systems. Now let us study this noise component YNT. This YNT, let us study this component. YNT is this thing. So I open the alpha minus beta, sine is sine alpha cos beta minus cos alpha sine beta. Then I can write this Vn sine phi nt. So what is Vn sine phi nt? I have just taken the envelope of the noise, multiply with its sine part. Alright, so this will become the quadrature component of the noise. I have taken the envelope, multiplied it with the cosine part of the noise phase. This is the in phase, NFS, NFC, sorry. This is NFC and this will be NFS. So I can write this NFS, this will be NFC. Now you can see here that what is phi of t? We know phi of t is kpmt, or if you take for fm, so phi of t is 2 pi kf integral mt dt. So it is actually proportional to the signal in pm or proportional to the integral signal, but in both cases it is a slowly varying signal because phi of t has just a bandwidth of w, the message bandwidth. All right, But what is the bandwidth of NC and NS? That is very, very important. Remember, we also studied this in the last chapter. What is NC and NS? You know, the noise is a band pass process when it is received at the receiver. So first of all, it is flat noise, a white noise. But once you pass it through a band pass, which restricts it to the frequency, to its BC or its Carstens bandwidth. So now you get two boxes. Yes. So after you have passed it through a band pass filter, this will be the phase of your noise. It will be around FC, but its bandwidth is BC. Its bandwidth is BC. Now, what is BC? You know, BC is the Carstens bandwidth, 2 beta 1 plus 2 into beta plus 1 into W. So, you know, if beta is 5, then 5 plus 1 is 6, 6 times 2 is 12. 12 into W. This is a very, very large bandwidth as compared to W. We have also seen in chapter 4 that the bandwidth of an FM signal is much greater as compared to the bandwidth of an AM signal. In AM signal, you have W or 2W, but here it could be 12W or 8W, a very large W. Okay. Say FM signals have large bandwidth as compared to AM signals. So this is a large bandwidth. Now, when I will, this is my band pass. Now, when I want to represent its low pass that we studied in chapter 5, what will happen? I will bring this at the zero frequency. I will also bring this at the zero frequency. So when I brought both of them at the zero frequency, the height will become N0, N0 by 2 plus N0 by 2. This will become N0. And the bandwidth will be, but the bandwidth, you know, the width will be actually BC, but this will be negative frequency, this will be positive frequency. So bandwidth will become actually BC over 2. All right, because bandwidth is a range of positive frequencies. अच्छा, इसके कोई क्वेश्चन है?
सर
एक बंदा कोई क्वेश्चन कह रहा है, ये आपने भेजा?
सर
हाँ जी जी, आप कुछ कह रहे हैं जी
सर? वो नोटिस भेजा सर, वो हमने सर चैट में, आप वो देख लें प्रीरेक्विजिट।
हाँ, ये अरम अशफाक साहब ने भेजा है ना, मैं इसको पढ़ लेता हूँ। अच्छा, नहीं ये आप इसकी बात करें, इस मैसेज की बात कर, मतलब मैसेज कह रहे हैं, इसकी बात कर रहे हैं आप, इस ऑर्डर की?
जी सर।
ये तो आई डोंट थिंक कि इसको कवर करेगा आपको।
नहीं सर, हो गया है इसका सर। बाकी सब्जेक्ट्स जिस तरह वो डिजिटल सिग्नल प्रोसेसिंग है, उसके प्री रिक्विजिट सिग्नल्स है, तो उन्होंने उसको भी सर कर दिया, वेव ऑफ कर दिया।
नहीं वो तो हो जाएगा, मगर आपने लगता है पढ़ा नहीं गौर से इसको।
नहीं सर,
लिखा हुआ क्या है? Moreover, the prerequisite for spring will only be waived off if the prerequisite was not offered in the fall 2020.
सर आपको इसी वजह से उस पर कहा था कि मतलब उसका मुझे आइडिया नहीं है कि सब्जेक्ट्स ऑफर कौन से हो रहे हैं नहीं।
अल्लाह के बंदे, फॉल 2020 में तो आपको ऑफर हुआ है प्रोबेबिलिटी
जी
तो
सर,
इसीलिए वेव ऑफ नहीं हुआ ना आपका। वेव ऑफ होना था अगर प्रीरेक्विजिट ऑफर ना होता। आपका तो प्रीरेक्विजिट कॉमन ही वो था, प्रोबेबिलिटी तो ऑफर हुआ है 2020 में।
सर
ये तो ऑर्डर मैंने पहले भी देखा हुआ है,
इसी
इससे
तरह
बात निकलती।
सर इसी तरह ही फिर जो सब्जेक्ट्स ऑफर हुए हैं उनका फिर वेव ऑफ नहीं होगा।
हाँ, मतलब जो जिनका प्रीरेक पिछले सेमेस्टर में ऑफर हुआ है उनका प्रीरेक वेव ऑफ नहीं होगा, मगर जिनका ऑफर नहीं है उनका वेव ऑफ हो सकता है। वो तो यहाँ पे लिखा हुआ है, ये तो मैंने ऑर्डर देखा हुआ था। बहरहाल मैं इन बातों में आगे नहीं जाना चाहता, जाहिर है ये तो आप बात कर लीजिएगा, मगर इसके मुताबिक आपका वेव ऑफ नहीं, उन स्टूडेंट्स को नहीं एडमिट करेंगे जिन्होंने प्रोबेबिलिटी पास नहीं किया। ठीक है, लेट्स गो, हम चीज़ों में टाइम ना ज़ाया करें, हमें लेक्चर करना है। सो ऑलराइट, सो आई वाज ट्राइंग टू एक्सप्लेन वेरी वेरी इंपॉर्टेंट थिंग that what is the baseband or low pass noise. So both the quadrature and the in phase noise are just that you have brought the negative and the positive part of the band pass noise to low pass frequency. That is why its heights become double. ठीक है, अब देखिए यहाँ पे वो क्या कह रहा है। Let us try to understand this thing. So it is saying that NC and SS, ठीक है, we know they are slowly varying signals. They are low pass, you know, yes, they are low pass, but what is phi t? Phi t is the message, it is just a bandwidth of W. But NC and NS, this is NC and NS spectrum, its bandwidth is BC over 2. And you know, BCO2 is still much greater than W. It is 12W, 6W. All right. So remember that yes, they are low pass, but they are still very high as compared to phi t, because phi t is the original message signal or proportional to the message signal, while NC and NS are the low pass version of the high pass band pass noise. Okay. Which are the infinite quadrilateral of the band pass noise at the receiver and have a much higher bandwidth than, yes, much higher bandwidth than phi t. In fact, the bandwidth of filtered noise, the demodulated output is half of the bandwidth. Yes, you know, the bandwidth of the filtered noise at the demodulator's input is half of the bandwidth of modulated signal. This we have just saw. Here the bandwidth of BC, but once you make it low pass, its bandwidth becomes half. Okay. Therefore, we can say that when we compare variations in NC and NS, they are quite greater as compared to phi t. So we can just assume phi t is just phi, a constant angle. Hence your y and t comes out to be this thing. So phi t comes phi, very low pass signal as compared to NS and NC. So this will be your noise, y and t. Now is everyone understanding? How do we get this noise? All right. Now, here we should remember that what about this band pass noise? Band pass noise, as seen here, it is symmetric with respect to FC and minus FC. It is symmetric with respect to FC, that we can see. And we have seen in chapter 5, in the last example, when we were studying that chapter, that when FC is the axis of symmetry of the band pass noise process, as we have seen that FC and they are the axis of symmetry. Therefore, the condition that led to the result of example 5.3.3. So, if you see that example, let us just have a revision, but we have done that example. So, I was not needed to revise it, but just for sake of your understanding or complete understanding with no confusions, I just want to show that particular example. Yes, this was the example, and we have done that. So it said that if band pass white noise is the output of the filter H1 of F given in so this H1 of F was this thing. This was H1 of F. It was the ideal filter. Okay, around FC with bandwidth of WW. Right. This was your H1 of this was your H1 of F. All right, around FC bandwidth of WW, negative and positive. Okay, find the power spectral density of the process ZT, which is equal to AXCT plus BXS, where XC was the low pass version of X, of band pass X, and X of S is again the low pass version, but the quadrature component of the band pass process X. Okay, that was studied in the last chapter. So we saw that if FC is the axis of symmetry, the in phase and quadrature components will be independent. So once they are independent, their correlation will be 0. And we have seen another example when their correlation is 0. So if you could see another example, we have studied also already earlier, that if you have a sum of two processes where the two processes are uncorrelated, then in that case, yes, actually the power density comes out to be this thing for sum of two processes. But if they are uncorrelated, then this their autocorrelation is just the product of their means. Okay, and as the processes are of zero mean, for example noise is zero mean, so in that case this RXY is 0, and this similarly if autocorrelation is 0, then it's its Fourier will be definitely 0, or the cross correlation of XY is 0, so the PSD of that cross selection will also be 0, and hence your power spectral density of the sum process when the two processes are uncorrelated with one another comes out to be sum of their two power spectral densities. Just sum of their two power spectral densities. Okay. So applying the same fact in the last example that we have studied here. So the PSD of this will be PSD of this into PSD of this. All right. So you know the PSD of this, that this will be whatever the band pass brought it to the low pass, double the height. This will be also same, but this is being multiplied with A, and you have to find its PSD. So you know this will become you multiply this with this will become A square into this PSD. This will become B square into this PSD, and then you know the PSD of the quadrature and the in-phase comma, they are the same. As we see, both come in the low power, height is n naught, both of them. So I can just replace them by S of x. All right, and A square, so S of x is common. This becomes A square plus B square. So for a sum process, I can write the output as A square plus B square S of x f. All right. So if I apply this same thing here, this signal, so it will be what? PSD of this into PSD of this into whatever the constant term which was A or B. This will be cos square over AC square. This will be minus sine whole square over AC square. So this will become sine square. So this will be cos square plus sine square over AC. And you can see AC comes out to be common, and cos square plus sine square is 1. So your power spectral density comes out to be SNC, or the spectral density of NC. You can also write NS, both are the same, divided by AC square, where SNC is the power spectral density of the in-phase component, but you can also write this as SNS because the power density of both of them are same. All right, and here you can see yes, the filtered noise, the band pass process, it extends around FC with a bandwidth of BC. You can see BC, negative to positive BC bandwidth. So, but the in-phase and the quadrature component, that will be N naught, and its bandwidth will be actually BC over 2. But you know, for negative positive, it has negative BC there and negative BC over 2, as I just showed you here. This is the band pass, and this is the low pass with double the height with minus 2 plus BC over 2. Okay, this is all that. So we have found the value of this SNC. So I just put this value of SNC, which is the height of N naught, in this equation. So SYFN comes out to be N naught over AC square, and the bandwidth is restricted to BC over 2, but negative to positive, it goes from minus BC over 2 to plus BC over 2. So this provides an expression for the PSDs. We have just driven this expression. Now, what will happen that after demodulation, you know, another filtering will be applied, as you have just seen, because this bandwidth is going up to BCO2, but BC, you know, it is Carson's bandwidth, which is very high as compared to W. So I have to apply a low pass filter that will restrict its bandwidth to W, because the message signal is only present in the W bandwidth. So no need for this large bandwidth. So I will pass it through a low pass filter of W bandwidth to get the output. In FM, we also saw that YFNT is actually first differentiated and then scaled by 1 or 2 pi. In NPM, YN is just added. But in FM, we just saw YFNT is firstly differentiated and then it is divided by 2 pi or scaled by 1 over 2 pi. And we know, all right, you are passing your YNT through a differentiator. So YFNT is a random process. It goes through a differentiator. So what will be the output? We have seen output is actually HF mod square. Whatever the filter, it is mod square times the power spectral density of the input process. So input process power spectral density is SYN, which we have just found here. This SYN, but HF of differentiator, we know it is, J2 pi F, times the input. So input is there, but J2 pi is HFF. But for a random process, the output will be HF mod square into the PSD of the input. So HF mod square will come out to be 4 square, J square, pi square, and all that. But mod also, J square is now -1, but mod will take it out. So this will be 4 pi square F square. That, all right, that 2 pi F comes out to 4 pi square F square into SYN, and that and then 1/2 pi is already there, so it will also be squared. It will come out to be 4 pi square. हाँ जी, सबको ही समझ आ रहा है कैसे है ये टर्म? ये चैप्टर 5 मैंने इसीलिए पहले कवर किया ताकि ये हमें चीजें समझ आती जाए कैसे हो रहा है. हाँ जी सलमान साहब, आर यू अंडरस्टैंडिंग हाउ वी गेट दिस टर्म?
जी सर.
चलिए, गुड. So you can see 4 pi cancels, and you have F square into this thing, and we have found SYN. SYN we just found it was actually equal to N naught over AC square. We just saw here it is just N naught over AC square, N naught over AC square, and the bandwidth is again the half of the Carson's bandwidth. So this is the output PSD of the noise in FM, and the previous equation represented the output noise of the PM. So you can see in FM you are just multiplying by F square, and rest of it is same. So you can see that PM has a flat noise spectrum, flat, but in FM, because of F square, you have a probabilistic noise spectrum, or a parabolic, not a probabilistic, a parabolic noise spectrum. And you can see here, this is the spectrum for PM, noise in PM, and this is the spectrum for noise in FM system because of presence of F square. And this is the PSD. So if I can very well find the total power, I just integrate the PSD, I will get the total power. Okay. So I will pass this PSD of bandwidth BC or bandwidth BC over 2 or minus BC over 2 to plus BC over 2 through a low pass filter. So the output will be just going from minus W for both PM and minus W for both as well as for FM with this parabolic structure because of the low pass filter. Again, we are using low pass filter is ideal, so its height is 1. That is why this will all come up. So the total power. Hari, someone has any question? Hari Abdullah Afzal, have you any question? Or I will mute you so that we are not disturbed. All right. So we just integrate, how to find the power. When you know the PSD, you just integrate over that PSD, you get the total power N naught by A square into 2W, you will get this thing, and this will be N naught AC square into F square. So F square will be F cube over 3. So N naught 3 AC square comes here, and then F square will become F cube over 3. So F cube is W cube minus W cube, this will become plus 2W cube. This becomes FM, right? So we have found the output power of the noise in both PM and FM systems. So now what is the signal? In PM the signal is just Kp in empty. In FM the signal is actually Kf empty, as we just saw. The message signal is Kf empty for PM, and here it is Kp empty. So if I want to find its power, I will take its square and integrate. Kp square, Kf square will come out, and inside you have empty square integral, and empty square we know this is the power of the message signal PM that we have studied in previous chapters. So the SNR at the output of the receiver will be the signal power. This is divided by the noise power, both for PM and FM. So Kp square PM, this is the signal power, divided by noise power of PM, which you know was N0 over AC, was N0 W N0 over AC square, or 2W. So that 2W N0 will come in the denominator and AC will go in the numerator. AC square will go in the numerator. Similarly for FM, you have again this kf square PM will be the signal, and this will be divided by 2W square not W, divided by 3AC square, which will actually go into the numerator. As you can see, 3AC square will go into the numerator. So now the signal to noise power at the output of your receiver or your demodulator, and then the low pass filter. This will be the signal to noise ratio. The answer is so, but we will be trying to look at different manipulations of the same signal. Now we can see that AC square is the receive power signal. We can denote this by PR. So in all the AM modulations, first we found signal to noise ratio at the output of the receiver. Then we represented the same signal to noise ratio in terms of the received signal's power, where the received power represented the signal at the input to the receiver. Remember, this is S over N output at the output of the receiver, but we just represent this signal to noise ratio in terms of the power received at the input to the receiver, so that you can compare various various modulation techniques in terms of the received power signals. So yes, the receiving power is AC square for FM and PM, because the what is FM and PM? It is just AC cos into all the phase. All right, the cos of phase, the cos of power phase just gives you a half. All right, AC cos, its power will give you just a half cos, and the rest of them will be AC square. So AC square over 2 is the overall signal power, or the received signal power. So I can say this AC over square over 2 is, this is PR. All right, and I also know that beta P is equal to Kp into MT, and beta F is equal to Kf MT, Kf into Kf max MT over W. This we have seen in the chapter 4, that you can find these betas as follows. So I will just replace my Kp square and Kf square by these beta values. So I just replace them by these beta values, and I've already replaced AC square 2 by PR, the received signal at the input to the receiver, and this is the signal ratio at the output of the receiver. Right? Here you can also say that PR N0 W, we know this is the signal to noise power of a baseband system. We have studied a baseband system in which there is no modulation and demodulation. Signal is just sent over the baseband and is received at the same baseband. So I just write PR and W as the signal to noise ratio at the baseband, so I can compare my output signal power with the signal to noise ratio at the baseband, as we have compared this in terms of AM modulation, amplitude modulation systems. Again, you can see what is PM over max MT square. PM is actually integral MT square. We have seen 1 over T infinity to infinity, T over 2, T over 2, all that we have seen many times, integral MT. But if we divide this by max MT, this becomes normalized signal, and square, this will be MT over its maximum whole square. This will be the MN signal, MN square signal, or the normalized signal. All right, so I can very well write this as PMN, or the normalized normalized signal. All right, normalized message signal, and so PMN will represent the power of the normalized signal. You have just taken this max MT square into the expression of PM. This very well as the taking max MT inside, this will become the power of the normalized signal. All right. Now again we can apply a little bit manipulation, that what is beta? We know that the Carson's bandwidth is 2 beta plus 1 into W. All right, both for PM and as well FM. So I can write this BC over W, which can be said that BC is the bandwidth of FM or PM, and W is actually the bandwidth of the message signal. So this ratio comes we can call this as the bandwidth expansion factor. All right, bandwidth expansion factor, and this comes out to be 2 beta plus 1, hence beta comes out to be bandwidth expansion factor over 2 minus 1. So I can replace my beta with this bandwidth expansion factor. Here he is again written this PMN as PM over max MT squared is same. You might write or you might not write. This can be taken both ways. So actually these are just the various forms of expressing your S over N. Main derivation was up till this point. This was synchronization at the output of the receiver. All right. And these are various, manipulations of the same representation so that we could study the effect of the various parameters on the synchronous ratio at the output of the FM or PM receiver. So we will end our lecture at this point. All the various, various, understandings or various driven points that can be driven from these expressions, we will be discussing them in the next lecture. So if someone has any question, you can ask.
सर एक क्वेश्चन था ये जैसे आपने वो उसकी सिंक स्केट की फॉरियर ट्रांसफॉर्म करवाई है, तो अगर एग्जाम में ये आएगी तो क्या हम सिर्फ बता सकते हैं कि इसकी ये फॉरियर ट्रांसफॉर्म ये करनी पड़ेगी पूरी?
आप दोबारा पूछें, थोड़ा सा आप जल्दी बोले, मुझे आवाज शायद क्लियर नहीं हुई, नेट भी है ना। आप क्या पूछें, दोबारा पूछें।
सर वो आपने सिंक स्केट वाली फॉरियर ट्रांसफॉर्म करवाई थी ना कि सिंक स्केट की फॉरियर ट्रांसफॉर्म एक ट्रायंगल होती है, तो एग्जाम में अगर इस तरह का कोई क्वेश्चन आता है जिसमें इस तरह की कोई ट्रांसफॉर्मेशन है फॉरियर ट्रांसफॉर्म में जैसे सिंक स्केट है, तो क्या हम इसको डायरेक्ट बता सकते हैं कि ट्रायंगल है या वो करनी पड़ेगी ड्राइव वहां पे?
नहीं, आप यूज कर सकते हैं कि ट्रायंगल का सिंक स्क्वायर होता है या सिंक स्क्वायर का ट्रायंगल होता है, ठीक है। तो मतलब या तो फिर ये हो ना कि उन्होंने सवाल में लिखा हो कि जी इसका फॉरियर ट्रांसफॉर्म निकाल के दिखाएं, तो फिर तो ठीक है, आप कॉन्वोल्यूशन करें और आप ट्रायंगल बना के दिखाएं कि ट्रायंगल बनता है। अगर वो इस तरह से पूछें, वो पूछ भी सकते हैं, वैसे पूछा नहीं जाता अमूमन, ये तो नेक्स्ट लेवल का कोर्स है, वो सिग्नल सिस्टम का पार्ट था, तो ऐसा सवाल अमूमन तो नहीं, मगर पूछ तो सकता है कोई बंदा, मैं उसको नो भी नहीं कर सकता, मगर कम चांस हैं इस तरह के सवालों के। मगर ये असल मैं जो समझा, मैंने जो इतनी आपको डेरिवेशन दी वो मकसद ये था कि मैं सिग्नल सिस्टम में जाऊँ। माई मेजर ऑब्जेक्टिव वॉज टू अंडरस्टैंड द रिलेशनशिप between the triangle and its bandwidth. If you write triangle of f, remember that its bandwidth is actually 1 for positive frequency, but there is also a negative 1 there. Okay? But for example, if I shift my triangle to some higher frequency, then remember that the triangle's bandwidth will be actually double as represented with respect to its mathematical representation. That is the difference between a rect and a triangle. Okay, that is very important for our understanding communication systems. Okay, so because of convolution the bandwidth becomes double, and that is the reason. So my main emphasis was to make this concept very very clear, because लेकिन अब आपको रेक दिया हुआ है या ऑटो कलेक्शन होगा, आपने उसका तो बता दिया ट्रायंगल, मगर अब उस ट्रायंगल की इंटरप्रिटेशन बड़ी जरूरी है। अगर उसमें कहा जी उतनी नॉइज पावर आपने देखनी है, तो हर में आपको बैंडविड्थ का कॉन्सेप्ट बड़ा जरूरी है, उसकी बैंडविड्थ कितनी है। आपके पास रेक्ट ऑफ टी आ गया ना, अब या रेक्ट ऑफ या जो ट्रायंगल ऑफ एफ आ गया, तो उसकी विड्थ क्या है, और फिर उसकी मतलब अगर दूसरा कोई यूज़र आपने बिठाना है किसी और फ्रिक्वेंसी के ऊपर, तो उसमें कितना फासला होना चाहिए, उनसे नॉइज़ कितनी निकलेगी, उसकी टोटल बैंडविड्थ कितनी है, ये चीज़ें कंफ्यूज करती हैं अगर आप सिर्फ रेक्ट के कॉन्सेप्ट को लेके चलें। तो मेरा तो मेन मकसद यहाँ था, मगर ठीक है, मतलब कि सिग्नल सिस्टम के सवाल पूछे जा सकते हैं, ये तो नहीं कि चैप्टर 2 भी इस कोर्स का वैसे तो हिस्सा है, तो मगर ये कि ज़ाहिर है मेन एम्फेसिस तो बेसिकली ये सिग्नल सिस्टम्स के कॉन्सेप्ट्स को कम्युनिकेशन में लेके आने का, तो मतलब कि मतलब इम्पोर्टेंस नहीं है, बट इट कुड बी आस्क्ड, दैट इज व्हाई आई हैव एक्सप्लेन्ड एवरीथिंग। यू कैन जस्ट कन्वॉल्व टू रेक्ट्स, यू विल वेरी वेल गेट अ ट्रायंगल। हमारी समाज जवाब समझ आ गया?
जी सर क्लियर है। मैंने बस ये पूछना था कि अगर किसी बड़े क्वेश्चन का पार्ट है तो मतलब कि कम्युनिकेशन क्वेश्चन नहीं है, लेकिन इसमें ये फॉरियर ट्रांसफॉर्म फाइंड करनी है, तो बस हम मेंशन कर देंगे कि इसकी फॉरियर ट्रांसफॉर्म है।
उसमें जरूरी नहीं है, या तो स्पेसिफिकली वो कहे ना, जैसे बहुत दफ़ा हम कहते भी हैं, क्योंकि ना मसला क्या है, स्टूडेंट से आप जॉब में इंटरव्यू लेते हैं तो अब उनको वो सबसे पहले यही बनाते हैं जी मेरे ये कंपनी है, उसकी ये बैंडविड्थ, अच्छा इसका टाइम डिपेंडेंट सिग्नल क्या होगा, अच्छा ये मेरा सिग्नल है, इसका बैंडविड्थ क्या होगी। अब स्टूडेंट जो हैं जो बिल्कुल ही जीरो, तो वहीं रह जाते हैं, इसलिए थोड़ा सिस्टम को इंपॉर्टेंस देते हैं कि चलो कम से कम ये तो पता ना कि उसकी PhD होगी और कब उसका फोरियर ट्रांसफॉर्म होगा, अब वो भी कंफ्यूज स्टूडेंट्स हो जाते हैं। अब कहते हैं जी रैंडम प्रोसेस है तो बताएं इसका स्पेक्ट्रम बनाएं। अब स्टूडेंट्स जो हैं वो सादा सादा बनाने लगते हैं, उसका फोरियर लेने लगते हैं, हालांकि रैंडम प्रोसेस में तो आपको PhD लेना पड़ेगा, ऑटो करेलेशन का फोरियर। तो ये छोटी छोटी चीज़ें हैं जिससे आपको पता है कि जो जिसने जॉब में अगर मेरिट पे हायर करना है तो उसने ज़ाहिर है छोटी छोटी चीज़ें चेक करनी है। अब ज़ाहिर है वो पूरी मैथ तो करने से रहा, 10 मिनट होते हैं उसके पास, उसने कॉन्सेप्ट्स को चेक करना होता है। तो कॉन्सेप्ट ज़ाहिर है सिग्नल सिस्टम से स्टैम्प करके फिर किसी कम्युनिकेशन सिस्टम पे अप्लाई होते हैं। तो हम ज़ाहिर है कि ये छोटे मोटे कॉन्सेप्ट्स को भी साथ लेके चलते हैं ताकि स्टूडेंट्स जो हैं वो मतलब कि क्लियर कर सकें वो बैरियर जो है जो एक कंपनी है जो भी है एक इदारा सेट करता है। तो इसलिए मैंने कहा था कि चलें वैसे तो नहीं पूछा जाएगा, मगर अगर फर्स्ट ये भी पूछा, बहुत दफ़ा हम करते भी हैं कि जी ये देखें ये आपको सिंक स्क्वायर है, इसका ज़रा ड्रॉ करें ना स्पेक्ट्रम। वो इसलिए रखते हैं कि वहाँ जब उसको कहा जाए ड्रॉ करने को, अब जैसे मैं जब लम्स में गया तो पहला हालांकि वो मतलब PhD के इंटरव्यूज़ थे, मैं स्कॉलरशिप पे सिलेक्ट हुआ था, फिर उन्हें लेना था इंटरव्यू तो लेते हैं, ज़ाहिर है कि भाई कुछ ना हो चेक डबल चेक। तो आते ही सिग्नल सिस्टम शुरू हो गए। तो ये सिग्नल सिस्टम सारे जो 12 टीचर्स बैठे उनके लिए कॉमन है, सिग्नल सिस्टम सबको ही आता है अगर वो कॉमन सिग्नल प्रोसेसिंग में जा रहे हैं आप, तो है ही इंपॉर्टेंट। तो सारे मुझे मुख्तलिफ सवाल पूछ रहे हैं। इवन तो मेरे PhD क्वालिफायर जो लम्स उसमें भी मुझसे उन्होंने एक है डेल्टा फंक्शन का चक्कर है बड़ा मशहूर मैथ, वो उस पर काफ़ी घुस गया मेरे ऊपर। तो सिग्नल सिस्टम में ऐसी चीज़ें जो आपको जान नहीं छोड़ती, चाहे आप कम्युनिकेशन में जाएँ या कंट्रोल में, जो सिग्नल प्रोसेसिंग वाले जहाँ इंपॉर्टेंट है कि आप जहाँ सिग्नल से खेल रहे हैं। सो दैट इज़ वाई इट कुड बी आस्क्ड, सो यू शुड नो योर बेसिक्स, सही है, as well as their application to communication systems. So I'm sorry we have taken a lot of time, maybe मैं देखा नहीं कितनी देर हुई, 2 मिनट ऊपर हो गए. So I will end the lecture here. So please clarify, because this order does not clarify that you can take up this course if you have not passed the previous course. All right, thank you very much.